This webinar is designed to provide customers with a resource on how to review run data and troubleshoot issues that may appear on the NextSeq 550. We also hope this will empower NextSeq 550 users to be comfortable with unexpected instrument situations and to perform best practices. We'll briefly discuss general information regarding the NextSeq 550 technology, available control software, how to perform a system check in Proactive. Next, we'll go over some common errors that occur before the run is started and how to troubleshoot these. Then we'll go over run metrics to determine what a good run looks like and also review some of the most common issues observed during NextSeq runs. Lastly, we'll go over post-run management and instrument maintenance. Here's the NextSeq 550 technology. The NextSeq has 6 parallel imaging modules and uses 2-channel chemistry. The sequencing by synthesis, or SBS chemistry time, completes in about 1.5 minutes. The sequencing chemistry for the NextSeq is isothermal at 60 Celsius, so the entire run is at a constant temperature. Also, there's no chiller compartment on the instrument, so reagents are stable at room temperature for up to 24 hours. Fluidics are performed using a valve and stagger method, which allows for a shortened runtime. Let's review how 2-channel chemistry compares to 4-channel chemistry. The HiSeq and MySeq use 4-channel chemistry, while the NextSeq, MiniSeq, and NovaSeq use 2-channel chemistry. In 4-channel chemistry, each base has a different frequency of color because there's a separate dye for each of the 4 bases. 4 images are taken using 4 different wavelengths to determine each individual base. 2-channel chemistry works by using only 2 images and 2 wavelengths, red and green, to determine which base represents each cluster. If only green intensity is detected, this is a T. If only red intensity is detected, this is a C. If both red and green intensity are detected, which is shown as yellow, this is an A. And if no intensity is detected, this is a G. With only 2 images taken as opposed to 4, each cycle can be completed in less than 5 minutes. NextSeq optics use 6 parallel cameras as indicated on the left. The numbering of the cameras moves counterclockwise, with each camera covering 1/3 of 2 of the lanes. The camera section layout can also be visualized in the SAV chart, which is shown in the middle image, with the different sections representing each camera. And the image on the right shows an actual NextSeq flow cell. As mentioned before, fluidics are performed using the valve and stagger method, which reduces sequencing time. This method allows for 2 lanes to be imaged, while the other 2 lanes concurrently perform SBS chemistry so that fluorophores are incorporated for the next cycle. In this example, lane pair A, which is lanes 1 and 3 shown in pink, are performing fluidics with SBS chemistry, while lane pair B, which is lanes 2 and 4 shown in blue, are imaging. The direction of fluid flow for the 2 sets of lane pairs is different. For lane pair A, the inlet is at the top and the outlet is at the bottom. And for lane pair B, the inlet is at the bottom and the outlet is at the top. The picture in the middle and right indicate the same lane pairs in both a high output and mid output flow cell, with the 2 lane pairs corresponding in pink and blue. Here are the single-use consumables for a NextSeq run: the flow cell, the SBS reagent cartridge, and the buffer cartridge. The latest version 2.5 flow cell, is shipped at room temperature, but should be stored in the fridge at 4C. The SBS reagent cartridge is stored at -20C and can be thawed in a room temperature deionized water bath for 60 minutes and can then be placed on ice or set aside at 4C for up to 6 hours. Alternatively, the SBS reagent cartridges can be thawed overnight at 4C and then stored in the fridge for up to 1 week. The buffer cartridge is shipped and stored at room temperature. For more recommendations and best practices for storage and thawing of consumables, please see the link to the bulletin here. The reagent cartridge includes all the reagents for clustering, sequencing, and paired-end turnaround. There are also empty wells in the cartridge, which are wash reservoirs used during the post-run wash once sequencing completes. Position 11 already contains bleach that will be used for the post-run wash. Custom primers that require their own location should be added to positions 7, 8, and 9, and these need to be indicated during run setup. If not selected, the instrument will instead pull from the standard primer wells in positions 20, 21, and 22. Custom sequencing primers can also be spiked into the Illumina primers, and here is a bulletin with this information. Currently, there are 2 versions of the NextSeq Control Software, or NCS, available, version 2.2 and version 4.0. If your instrument has an older version of NCS, I recommend manually upgrading to version 2.2 so that version 2.5 flow cells can be recognized. Version 4 software will come on newly installed instruments as well as recently upgraded NextSeq DX instruments. If you would like to upgrade to NCS version 4, please discuss the upgrade with your field team. The upgrade is free if the instrument is on an active warranty and is a paid upgrade for instruments not on contract. Please call tech support for any questions. Here are some features available in the NextSeq Control Software version 4. The upgrade changes the operating system from Windows 7 to Windows 10, which requires a hard drive change that must be performed by an Illumina engineer. The V4 upgrade also includes a new version of real-time analysis, RTA, and introduces Local Run Manager, LRM. LRM is used for run setup, monitoring, and downstream analysis, and is also available on the iSeq, MiniSeq, and recent versions of the MySeq. Previously, PrepTab on BaseBase was used for setting up runs, but PrepTab will no longer be compatible. With NCS version 4, LRM is used instead, but runs can still be sent to BaseBase for run monitoring, storage, and analysis. For LRM analysis, modules will need to be manually installed, and these can be downloaded from the Illumina website. If a NextSeq DX had been updated to at least version 4.0, the RUO mode will recognize version 2.5 flow cells. And here are links to 2 bulletins with frequently asked questions and what to expect when upgrading to NextSeq Control Software version 4.0. Technical support will often ask you to perform a system check to assess the instrument performance, and here's how to perform a system check on the NextSeq. In the Control Software home screen, select Manage Instrument, and then System Check. This will take you to the NextSeq Service Software, or NSS. Note that if you have NextSeq Control Software version 4.0 or higher, you will need to have LRM login credentials to access the service software. And if you don't have an LRM account, you will be unable to log in to perform the system check. If you can perform a desktop share, tech support can log in and bypass this, or you can create your own LRM credentials and enable user management, as shown here. In LRM, go to Tools and select User Management, then enable User Management, create an admin level account, and create a temporary password. When logging into LRM, you'll be prompted to change the temporary password to an updated password. Now you will have an admin level account that can be used to log into the service software to perform a system check. Once you're in the service software, the motion, fluidics, and thermal tests are pre-selected. Note that the optics tests require a special flow cell from an engineer, so we recommend leaving them unchecked. The system check is automated once started, takes about 90 minutes, and uses a used high output flow cell. Illumina recommends a high output flow cell since mid-output flow cells can have false failures. The buffer tray should be loaded with 120 mils of lab-grade water in the center reservoir, and the other trays should remain empty. Once complete, a results screen will show pass or fail for each test, and detailed results can be found in the D drive, as shown on the slide. If there are any failures, please reach out to tech support for further review. I highly recommend using Proactive. Proactive is a free service that collects run metrics data from the instrument and sends it to a secure network. This service collects run metrics only and does not transmit any sequencing data or personal information, such as sample information or BCL FASTQ data. Proactive is useful because it gives Illumina quick access to run performance information so we can assess sequencing runs and help troubleshoot. Additionally, we have algorithms monitoring instrument performance metrics that are designed to detect potential issues before they impact sequencing runs, which prevents sequencing issues and instrument downtime. Here are some Proactive resources. You can also use your Mylllumina account to view historical trends for performance and usage. Note that Proactive requires that the instrument be connected to a network with internet access. Let's go over some of the most common NextSeq pre-run errors that can occur during run setup. Please try these troubleshooting steps, and if the issue requires further assistance, please call or email Illumina technical support to troubleshoot together. Even if the issue is resolved, please contact tech support so that we can properly document the issue and also so that we can replace any reagents if they're warranted. An RFID consumable error occurs when loading the consumables for a run. Unlike the MySeq, if the RFID is not detected, there is no bypass code that can be added as a workaround. This error can be related to an RFID issue with the consumable or a communication issue with the sensor. If observed, reseat or reinsert the consumable. If the issue persists, power cycle the NextSeq to restore a possible communication sensor issue. If reseating and power cycling do not resolve the RFID error, load another consumable. If none of these resolve the issue, this could indicate the RFID sensor on the instrument is not working and a field service would be required. The spent reagent container error can appear when the spent reagent container is full or cannot be detected, which can occur during run setup or during the run. This can be related to the container being full, a communication issue, or the waste sensor being dirty. If the waste container is full, empty it, reinsert it, and then proceed with the run. If the message still appears, remove the spent reagent container and check the top of the waste container as well as the waste container sensor, which is shown in the image. Then clean the container and the sensor using a lens paper or Kim White. If the issue persists, power cycle the instrument to reset communications. If there's another NextSeq available, you can also swap the spent reagent containers. If the issue is still not resolved, then a field service visit is required by an engineer. The fail to find Fiducial message occurs during the pre-run check, right when the run is about to start. During the pre-run check, the instrument looks for fiducials or marks on the flow cell, and sometimes these are not found during flow cell registration. These fiducials are not related to clustering and do not affect run performance. The flow cell has 6 fiducials, and as long as one is detected, the run can start. So as long as one camera is detected, please acknowledge this message and allow the run to begin. If there are no issues with the run, power cycle before the next run. Fluidic automation errors can occur at any time, such as at initialization, during a wash, during a pre-run check, or during a run. These errors are numbered and are related to a hardware component. If this error occurs during a run, the run may stop prematurely. Power cycle the instrument, and if the instrument initializes successfully, perform a system check. If the system check passes, the instrument can be used again. If the error appears again at any time, please let tech support know so an engineer can service the instrument. This imaging system failure message appears during the pre-run check and indicates either a communication issue or that the flow cell is not seated correctly. First, go back to the loading step and reseat the flow cell. If the error persists after reseating, go back to the loading step, remove the flow cell, and exit to the home menu to power cycle the instrument. Removing the flow cell is recommended because if the flow cell was loaded during initialization, there could be difficulties removing the flow cell. Once initialized, set up the run and load the flow cell again. If the issue persists, load another flow cell. If the issue still persists, a field service would be required. The flow cell registration issue appears after the upgrade to NCS version 4. During the pre-run check, which normally takes about 10 minutes, there's a delay during the flow cell registration check that can take up to 30 minutes. This increased time is due to the instrument downloading image drives. This wait is normal and only appears during the first run after the upgrade. Once complete, you will not experience a similar delay again. So please wait the 30 minutes. Sometimes it may ask to retry, and if this happens, power cycle and reseat the flow cell before proceeding again. Next, let's discuss evaluating a NextSeq run. To evaluate a run, Illumina looks at the Q30 scores, the time of the run, the amount of data output in gigabases, the cluster density, and the read passing filter. Each kit will have its own Q30 and output specification. The NextSeq has a high and mid output configuration with run lengths ranging from 75 cycles to 300 cycles. To determine the maximum number of cycles available in each kit, see these bulletins, which go over the maximum read length recommended on each sequencer. On the NextSeq, the maximum recommended read length is 151 cycles, with 20 cycles as the maximum index length. Illumina does not recommend runs going over the maximum cycle number of the kit or the maximum recommended read length, as they both can cause significant quality drops. To find the instrument specifications, go to the Illumina website main page, select Products, and scroll over Instruments. Then select Sequencing Platforms. This opens the Sequencing Platforms homepage. Scroll over Sequencing Platforms to bring up the instruments and select NextSeq 550. Now select Specifications. The Specifications page will show the main specifications, which are runtime, output data, read passing filter, and quality. There's an expected runtime range for each kit, and runs with less cycles will complete in less time. A high output 1/75 cycle run will take 11 hours, and a high output 2/150 cycle run will take just more than 1 day. If the runtime is taking longer than expected, please let tech support know, as this could indicate the computer is running slow, a lack of hard drive space, or possibly an issue with the run. Illumina recommends performing sequencing runs with at least 25 cycles in read 1 so that RTA can accurately calculate pass filter and other run metrics. For more information about why at least 25 cycles are recommended, see the bulletin here. Output or yield will vary based on the type of run, and runs range from 16 gigabases for a 2/75 cycle mid-output run to 120 gigabases for a 2/150 cycle high-output run. High-output runs have 3 times as many tiles as mid-output runs, so they have 3 times more data. Pass filter involves a chastity filter for each cluster and is a measure of cluster purity. The purer the signal, the higher chance a cluster passes filter. Single read high output runs have up to 400 million reads passing filter, and paired end runs can have up to 800 million reads passing filter. As with output, the amount of reads passing filter for a high output run is 3 times greater than a mid-output run. So a mid-output run will generate between 130 million reads passing filter for a single read and 260 million reads passing filter for paired end. Q30 is based on a Phred scale and corresponds to the chance of a base being incorrect. Q30 indicates a base call with 99.9% accuracy. This Q30 score is calculated after 25 cycles and is only based on clusters passing filter. Quality is dependent on read length, and longer runs have lower overall quality. For 2x75 cycle runs on both high output and mid output kits, the Q30 should be above 80%. For 2x150 cycle runs, Q30 should be above 75%. Note that these specifications are the average Q30 for the entire run. Here's a summary table of the different kits and the specifications for each type of run. Note that the optimal cluster density for a well-balanced library on both the high output and mid output runs is 170 to 220,000 clusters per millimeter squared. Sequencing Analysis Viewer, or SAV, is a software that can be used during or after a run completes to view detailed run metrics. SAV can be downloaded for free from the Illumina website linked here. The latest version is version 2.4.7, but version 1.9.1 or higher should properly display the NextSeq metrics. If there are issues downloading, please call or email tech support for assistance. SAV can be downloaded on your own computer or on the instrument. 3 files are required for SAV: the interop folder, runinfo.xml, and runparameters.xml, which are all in the run folder shown here. This data can also be observed on BaseBase, and the files for SAV can be downloaded from BaseBase. For more information on SAV, check out this recorded webinar called Sequencing Analysis Viewer, a Beginner's Guide. Here's an example of a NextSeq 150 cycle high output run in SAV. Data can be loaded by copying the file pathway of the run folder at the top, or by selecting the Browse button and navigating to the Run folder. To view the run metrics, go to the Summary tab. Here is the Summary tab with the run metrics such as yield or output, cluster density, pass filter, and Q30. Let's first look at the expected yield shown here in red. The 2x75 cycle high output run yield should be between 50 to 60 gigabases, and this run has about 60 gigabases, which is above the Illumina yield specification. Next, let's look at cluster density. For a well-balanced library, the ideal cluster density is 170 to 220. For this run, the cluster density is about 160, which is slightly less than the recommended range. Here is reads passing filter. To calculate the number of reads passing filter, look at the amount of reads in read 1 for each lane. For a single read run, add up all 4 lanes, which would be about 388 million reads in this example. For a paired end run, double that amount, which is about 777 million reads in this example. Last, let's look at the Q30 score. For a 2x75 cycle run, greater than 80% Q30 is the Illumina specification. For this run, 97% Q30 was obtained, which is well above 80%. Overall, the run quantity and quality are above Illumina specifications, even though the cluster density was a little lower than Illumina's recommended range. To optimize this run, the loading concentration can be increased slightly to achieve a cluster density in the recommended 170 to 220 range. Now let's look into camera disabled errors that may occur during the run. The camera disabled error for multiple cameras is one of the most common errors observed after a run starts, and they usually appear about 2.5 hours into the run when cluster generation completes. This error is similar to a MySeq Cycle 1 error and can be related to the library, run setup, consumables, or instrument. So all these components need to be investigated further. As seen on the images on the left, a large number of notifications may appear, and then the run can stop with an error asking if you would like to save the flow cell. Illumina does not recommend saving the flow cell because it is unclear what caused the error, and a new reagent cartridge would be required. The instrument will then ask if you wish to purge reagents. The purge expels the sequencing reagents from the cartridge into the waste, but it can take several hours to complete. You can either purge the reagents or not, depending on the time or requirements from your EHS. A great feature with the NextSeq is if a Cycle 1 camera disabled error stops a run, the autofocus images can still be viewed and are found in the Images folder within the Temp folder. While reviewing these images in lanes 1 and 2, many images appear black, but there will also be images with clusters present. Lanes 3 and 4 will just have the clustered images. The 4 clustered images here show a range from severely low cluster density to very high cluster density. Clustering failure and severely low or high cluster density can cause a camera disabled error because the cameras cannot properly focus on clusters on the flow cell. So check these images as a first troubleshooting step. Since the Temp folder gets rewritten when another run begins, I advise saving these autofocus images to a location other than the Temp folder before starting another run. If no clusters were detected from the focus images, then this indicates a clustering failure. To troubleshoot, first review the library type sequence. All Illumina libraries are compatible with the NextSeq, but if third-party libraries were used, we would want to verify their compatibility with Illumina sequencing primers. If custom primers were used, verify that they were added to the correct location and were selected appropriately during run setup. Then, recheck the library loading concentration as well as the sodium hydroxide concentration and pH. To test the temperature, fluidics, and motion of the instrument, as well as the fluidics in the flow cell, power cycle and perform a system check using the same flow cell from the run or a high output flow cell. If there are any fluidic issues detected, such as a pressure decay or flow rate failure, another power cycle and system check with a different high output flow cell is recommended. If the system check passes, this indicates an issue with the original run flow cell. Once the system check is passing, the instrument is performing to specifications and can be used again. And if you're confident in the library, a rerun can be performed. If using an uncertain library, spiking in 20% Phi-X is recommended. Sometimes at cycle 1, several camera disabled errors can appear, but the run does not stop. These errors indicate that only certain parts of the flow cell and cameras were affected. In the example, part of camera 3, which covers lane 2, became disabled. When observed, these are suspected to be related to a communication error or cluster density issue. To troubleshoot, first look at the focus images to verify clustering and the cluster density. In the camera In the camera sections not affected by this error, check that the cluster density is in the appropriate range. If the density appears higher than expected, the camera disabled could be related to overloading. If the cluster density appears normal, then a communication issue is suspected. Before the next run, power cycle the reset communications and perform a system check to verify the instrument. If this appears frequently and the run is within the normal cluster density range, please let tech support know, since an engineer may need to inspect the optics, especially if the same camera is repeatedly affected. In some runs, a camera disabled error can appear. These are listed as a camera sensor disabled or camera sensor failure warning in the logs. The message can occur at any cycle randomly and is not camera specific. From reviewing the SAV data, an entire camera section is disabled. Here, camera 6 was suddenly affected at cycle 268 and remained disabled for the rest of the run. If first observed, allow the run to complete and monitor the run performance. Then power cycle before the next run. This error can appear randomly and has appeared in consecutive runs or not again until many runs after. This was found to be a firmware bug, and we recommend upgrading to NextSeq Control Software version 4, which has resolved the issue. Now let's evaluate an overclustered run, since overclustered runs may have high registration failure, high error rates, possible run loss, and no reads passing filter. Let's first go over the optimal cluster density for a NextSeq run, and the ideal cluster density is the same for both the mid-output and high-output kits. For a well-balanced library such as PHYX, the ideal cluster density is 170 to 220. For low diversity libraries, the cluster density should be less. And here's a link to the support bulletin with the recommended cluster densities. Here's an example of a run with high cluster density in the 270 to 280 range. Note that the clusters passing filter, shown here in green, appear much less than the raw cluster density, shown in blue. For a well-balanced library, the cluster density should not exceed about 220. At a high cluster density, clusters tend to overlap, which results in the individual cluster signal not being pure, which lowers the percent pass filter. Let's look at a side-by-side comparison of a high cluster density run and a targeted cluster density run. The left is the same run data from the previous slide, and the right is the same library, but with cluster density in the ideal range. In the high cluster density run, the Q30 is just slightly above 70%. But in the run with the ideal cluster density, the Q30 is significantly improved at 93%. Error rates tend to increase in overclustered runs compared to a normal cluster density run. Error rate is calculated when PHYX is present, and since the quality is reduced in overclustered runs, PHYX will not align as efficiently, resulting in higher error rates. For more information on PHYX and why it is used in runs, please see the bulletin here. Another phenotype observed with high cluster density is tile dropouts, as shown in the red box. Too much signal can cause tile registration failure, which results in the instrument being unable to quantify the data. This registration failure can show up at random points and is not tile specific, as indicated by the blue tiles on the right. To address overclustering, recheck the library quantification to make sure the loading was accurate. Check the library size, since smaller libraries tend to cluster more efficiently than larger libraries. Also check for primer dimers, since these smaller fragments can increase cluster density. If all of these are correct, it is possible the library has a high clustering efficiency, and it's recommended to reduce the loading concentration. For additional information on overloading and how this affects run quality, please see the TechNote and recorded webinar linked here. Next, let's look at under-clustered runs. Initially looking at this run data, the Q30 is high at almost 89%. The percent base plot shows a well-balanced library, and the percent pass filter is very high compared to the raw cluster density. Looking at the data by lane graph in red though, the raw cluster density is low, around 60 to 70. Looking at the run summary, the cluster density was calculated around 69, which is about 1/3 the recommended cluster density for a well-balanced library. Looking at the data amount, yield was about 51 gigabases when the expected yield of a 2 by 150 high output run is 100 to 120 gigabases. For one direction, about 400 million reads passing filter are expected, but here there are only 170 million reads. In an underloaded run then, the quality remains high, but the quantity is reduced. So if you're unsure about a loading concentration, I advise erring on the side of underloading and loading less so that the run will still result in high quality data, just less of it. To troubleshoot low cluster density, first recheck the library quant. Make sure custom sequencing primers are compatible, such as melting temperature. Verify the library size, since shorter libraries cluster more efficiently than longer libraries. The larger libraries may require a higher loading amount. Also check for secondary structures, since this can prevent binding, and these can be removed by performing a heat denaturation step prior to sequencing. Check the sodium hydroxide, and the pH should be at least 12.5 for proper denaturing and annealing to the flow cell. Too high of a sodium hydroxide concentration or not neutralizing with tris can prevent strands from binding to the flow cell. Next, make sure the reagents are not expired, since expired reagents can impact clustering. Also check the Phi-X alignment. If Phi-X alignment was higher than expected, such as spiking in 10% Phi-X and obtaining 90% aligned, this high ratio of Phi-X to library indicates a low library concentration or poor library binding. The Phi-X denaturing steps can also help troubleshoot the library, because if one is affected and the other is not, this can help pinpoint where the library denaturing issue occurred. Now let's review runs that have low nucleotide diversity. Nucleotide diversity refers to the proportion of each nucleotide, A, C, G, and T, at each position in the sequencing library. In SAV, we see this in percent base in the data by cycle chart. For a well-balanced library, each nucleotide is expected to be about 25%, as shown on the left. For a low diversity library, the percent base can be higher for a single nucleotide, and the right shows percent base up to about 70%. Since every library insert is the same in a low diversity library, there is an uneven proportion of bases represented at a cycle. Amplicon and reduced representation by sulfite libraries tend to be low diversity. In a low diversity library, clusters will fluoresce for the same base at the same cycle. With only one type of base identified, it is difficult for the camera to image and determine what the other bases are, which can result in an inaccurate cluster map. Good diversity has different colors at each cycle and can allow for each base to be classified and analyzed separately. Two low diversity runs. On the left, no Phi-X is added, and on the right, the same library has Phi-X spiked in. Without Phi-X, the percent base is up to 50% in a single base in the first few cycles, indicated in the red box. In that same region where the percent base was low diversity, there is a large decrease in the Q30 score. When Phi-X is spiked in, though, the base diversity is much better. The percent base is less than 40% and has a less sharp peak represented by an individual base. This even base distribution then results in no significant drop in Q30. And throughout the entire run, the Q30 remains high. I do want to point out that in these graphs, the scale on the right is much less than the scale on the left, with 60 as the lower value rather than 0. To improve a low diversity run, aim for the lower spectrum of the cluster density range, so 170 or less. This is needed because if one channel becomes oversaturated, the unbalanced nucleotide composition can affect template registration and eventually quality. Spike in Phi-X between 10 to 50%, and a lower diversity library will require a higher Phi-X spike in. An alternative to Phi-X is to use a diverse library, such as a whole genome library, since the added base diversity will assist with template registration and improve overall run quality. For more information on low diversity libraries, check out the webinar and bulletin linked here. Lastly, let's discuss post-run instrument management and maintenance. There will be a notification every 90 days when the air filter needs to be changed. The air filter can be purchased from your Mylllumina account using the catalog number here. The air filter can be changed on your own, and instructions are listed in the system guide. First, mark the frame to indicate the date it was changed. From the back of the instrument, press down on the top of the filter tray to release the tray open. Grab the top of the old air filter and pull it out completely. Then reinsert the new air filter. The air filter has an arrow that points toward the handle of the tray and is inserted as shown in the diagram in the upper right. The image in the bottom right shows an image of a warning sign stating that the air filter is not inserted correctly. Once inserted, the tray can then be closed and the old air filter can be discarded. Note that the older instruments may have a different air filter, and these instruments will not have a notification. For these, the location of the air filter is on the side, and the air filter is a different shape. So please check your instrument first before ordering the filters. Power cycling the NextSeq is important to reset communications on the computer. Illumina does not have hard guidelines for how often to power cycle, but I'd recommend at least once every week or two, or if you do not sequence often, power cycle prior to the next run. If communication issues are suspected, a power cycle is recommended. To perform a power cycle, go to the Control Software home screen and select Manage Instrument, then select Shutdown Options, and then Shut Down, which will shut down both the NextSeq software and instrument. Once shut off, wait at least 60 seconds before turning on the instrument by pressing the button in the front. This will boot up both the computer and then initialize the control software. There are two types of washes available on the NextSeq, a quick wash and a post-run manual wash. And these can be selected by selecting Wash from the home menu. The quick wash is performed every 14 days the instrument is idle or after a shutdown. This takes about 20 minutes and only requires a 0.05% tween solution that is placed in the buffer wash cartridge, as shown by the red arrow. The post-run manual wash is performed when the automatic post-run wash does not complete, such as when the run ends early with an error. This wash is the same length as the automatic post-run wash, about 90 minutes. This wash requires 1 ml of 0.12% sodium hypochlorite that needs to be loaded in position 28 in the wash cartridge, as indicated by the pipette tip in the bottom right image. The tween solution is also added to the reagent wash cartridge. Note that the sodium hypochlorite should be lab grade and not a household brand, because the concentration of household bleach is not accurate and could have contaminants. Also, if a wash stalls or takes much longer than expected, back out of the run setup and either restart the software or power cycle the instrument, since there was likely a communication issue. Lastly, do not use any ammonium-based cleaners on or around the sequencer, because they can impact sequencing runs, as shown in this bulletin. Here's a brief summary of the information provided in this webinar, specifically for the pre-run errors and troubleshooting, reviewing run metrics and SAV, run errors and troubleshooting, low diversity libraries, and instrument maintenance. Here are additional resources for the NextSeq 550, including the system guide, setting up a run, sequencing low diversity libraries, and the latest software. Here are more resources that include Windows 10, optimizing cluster density, and the recorded webinars. I highly recommend reviewing LRM version 2.0, SAV, and sequencing considerations for a low diversity library. Thank you so much for joining this webinar, and I hope it's been helpful for you.